So this is our fifth lecture, and so what we've been talking about is what we've done is we've been working with applications of the integral. Namely, the ones we've been working on right now are volume, and then we derived, at least sketched, a formula that gives us the length of a curve. So the fancy word for that is arc length. So this homework 2 is asking us to work out some problems here. Now, some of these problems are routine, but there's a few of these that are quite difficult. And so someone has asked, Michelle, I think was you, and that was, let's talk about number 2. A few people had emailed me about these problems as well, so let's look at them. So let's start with the second one. As I said, when you're doing these problems, the first thing I would highly encourage you to do is get a geometric intuition for what's happening. So if I look at this problem, I know that I have a curve and a line, and there's some region, and I want to rotate this region to get a solid. And so if perhaps I take this, so let's make this our line. Let me fix it. So what you have to understand is I'm not necessarily drawing this to scale, but with a little intuition and a little of our math background, we can at least get a good sketch of this line. So this might be the point 1, and let's call this height 2. We know that this line, y equals 1/2 x. Excuse me, I wrote that wrong. This is actually 1/2. So this is the curve, or I guess technically it's a line, but this is the line. Y equals 1/2 x. So we want to take this line and we want to look at the curve y equals x to the 4th. So I'll draw that in pink. So what does that curve look like? Well, x to the 4th, again, and by the way, if you're not sure how to graph these by hand, it's okay to say, okay, I'm going to go to Desmos and check it out. Now, these are two curves that you should know how to graph without much sort of work, but nonetheless, you know, you can always go to Desmos if you need some assistance. Now, what we know is we know the curve x to the 4th passes through the point 1, 1. So here's how I'm going to reason this. So if this is my point 1, 1, I know that this x to the 4th, this curve has to actually come through here. So it's going to look like this. And of course, it goes up like goes up like that as well. The point of interest, though, is this point where they intersect. And what I'm interested in, the region that I need to study is this little petal right here. That's the region that I'm going to rotate. So before we go anywhere, you need to make sure you're comfortable with how I got this. And I need to figure out what that point is, but I'll do that in a second. Does anybody have a question? Now, again, if you need to go to Desmos to do this, that's fine. No one's going to be mad at you for that. But I would encourage that you be able to do this without using technology. So we need to find this point right here. I need to know what this point is where they intersect. And so I can find that if I just do some algebra. I need to know when 1/2 x is equal to x to the 4th. And that equation is the same. If I multiply both sides by 2, that's the same as x equals 2x to the 4th. And I can rewrite this as 0 equals 2x to the 4th minus x. And that factors. Pull out an x, and you're left with 2x cubed minus 1. So from that little bit of algebra, I know what this point is right here. This point where they intersect is the cubed root of 1/2. So again, that might be some algebra that you guys need to work on. But the solution here to this equation, the solution is, pick a color we haven't used. This number right here is the cubed root of 1/2. And that's the solution to this. So there's two solutions. The first solution is x equals 0, and the second solution is x equals the cubed root of 1/2. So if you don't get this part figured out, then you can't solve the problem correctly. So it's important that you understand how I got this. Does anybody have a question? So this is a little bit of a tricky problem. It takes a little bit of, it's not just plug and chug. So once you figure this region out, the next thing you ask yourself is, what happens when I rotate it? Well, when I rotate it, it makes sort of like this little horn or sort of flower-like thing. It's hollow, so this is hollow. So again, you're going to have to use your imagination here. Nobody's saying that it's that obvious that it's what it looks like, but you kind of got to use your imagination to put it together. Does anybody have a question? Okay, now, once you figure out what the solid looks like, you ask yourself, okay, which one of these slices am I using? Am I using the disc method? Am I using the washer method? Am I using the shell method? And one of the key things I told you is to think about what axis you're using. And so we talked about this last week. I said if it revolves around the x-axis, it's often best to first try the disc or washer method. And you'll notice that if you think about it, that's actually screaming at you, because if I take a slice of this creature, that's exactly what I'm getting. I'm getting a washer. I'm getting something. My cross section looks like this. It's a washer. So this suggests the formula for the washer method. And what's the formula for the washer method? It is where you take the following. So this suggests the formula: volume equals pi. Well, let's be a little more specific here. We're going to integrate from 0 to the cubed root of 1/2. And then we're going to take the outer radius squared, and that's times pi, minus pi times the inner radius squared. Dx. Sure. Hold on one second, Michelle. Yeah. Do you have a question about this one? If so, please ask. I should have finished this sort of sketch of this. No problem. So this is the formula that should be our likely candidate. Now we just have to know what the outer radius is and the inner radius. So I'm going to pull the pi out of everybody. So if I go back to the previous picture, what's the outer radius? The outer radius is the distance from the purple guy, and the inner radius is the distance from the pink guy. So as long as I have my functions lined up correctly, this would be 1/2 squared, or 1/2 times x squared, minus x to the 4th quantity squared dx, which becomes a relatively straightforward integral. This is 1/4 x squared minus x to the 8th dx. Does anybody have a question up to this point? Okay, so to finish this problem, we just have to know how to integrate. I'm cheating here, so not cheating, I'm writing it incorrectly. So when I integrate this, this becomes 1/12 x cubed minus 1/9 x to the power 9. And I'm integrating from 0 to the cubed root of 1/2. And so I first plug in 1/2 to the power 1/3. But look at the powers here. So this is now, this becomes an exercise in, you know, elementary algebra, exponent powers or properties. This is 1/12. When I plug 1/2 cubed in, I just get 1/2. And then when I plug in 1/2 to the power 1/3 into 9, I get 1/2 cubed. And then when I plug in 0, it's just 0 minus 0. So that might be a step that some of you might not be as confident with your raw properties of exponents. and that's okay. So it might take a moment for you to sort of pick up what I'm putting down there. So if you have a question, please ask while you're thinking about that. I'll give you a moment to do so. Any questions? Going once, going twice. All right, so then what we have to do, it remains to be done, is we have to simplify this so we don't look like we don't know how to do our mathematics. So what do you have? You have a 24 in the one fraction. You have a 72 in the other one. So one way to do this is to pull out common factors. So for example, each one of these, I have a 1/8 over here, and I have a 1/8 over here. And I mean, again, I don't really care how you plan on doing this, but at the end of the day, if you do it correctly, this just simplifies to pi over 36. Unless I made an error, which is quite possible. Does anybody have a question about this? Again, this is 1/24 minus 1 over 72, and then so you get 1/36. Does anybody have a question or a comment? Okay, so let's move on. We talked about problem 3 last week. I fixed the typo in it. You can now solve it. Problem 3 is requires the shell method. So let me just get you started on that. So here you have the line 1/4 x. So when you plug 1 into this, we're worried about this particular region. So again, I'm not drawing this to scale. What is this point? This is the point 1, 1/4. And the region I'm interested in is this region that I'm going to shade yellow. And so when I rotate that particular region around the y-axis now, when I rotate around the y-axis, I'm getting this. So maybe we'll kind of give this a dotted line to give it try to give it some perspective. Sort of like this, maybe you want to imagine this as like a hockey puck with a sort of cone hollowed out of it. I don't know. But this is sort of the solid that you get. So I would try to tell you to think about this as cone hollowed out. Is one way my mind is thinking about it. Again, your imagination is extremely important here. And again, think about this, because when I rotate it around the y-axis, there's nothing rotating in here. So this is sort of like, imagine like a hockey puck or a disc with a cone sort of drilled out of it. It's one way to think about it. Maybe I can sort of use another color here to try to help you envision that. So you have like a, again, it's not the easiest for me to do this on. Anyways, no matter how you slice it, because this is rotated around the y-axis, probably the easiest way is to use the shell method. And so that means the volume is the integral from 0 to 1 of 2 times pi times x times 1/4 x dx. Which, if you clean up, is 1/2 pi integral 0 to 1 of x squared, which I think you guys can all finish. Any comments, questions about that? Please let me know.
Professor?
Yes.
Where did the 2 pi come from in the first part of it?
That's the shell method. So the shell method's formula is, the shell method is integral from a to b, 2 pi x f of x dx. So the geometric intuition here, and you'd have to go back and look at the notes from last week. The geometric intuition is that the 2 pi x is the circumference of the shell, and the f of x is its height. So again, you would imagine that I have some sort of slice right here, this vertical slice, and I'm going to rotate it around the y-axis. And when I do that, it creates what we call a cylindrical shell. So this has a little bit of thickness to it. And its height is f of x. And its circumference is 2 pi x. So again, you might have to go back into the notes from last class to look at the geometry of these shells. But if I were, Thomas, I think it was you that asked this question, if I were to take that purple sort of gum band looking creature I have, that's a cylindrical shell. If I were to slice it, take scissors and cut it and lay it down, its volume would be 2 pi x times f of x times dx. So that's sort of where the intuition for that comes.
Okay, thank you.
Yeah, so again, here's a good rule of thumb in Calculus 2. It's not the rule, but it's pretty common. If you rotate around x, try the other formula from the first exercise. That would be the disk method or the washer method. And if you rotate around y, you should probably try the shell method first. That's usually the good way of doing it. Any questions about this? Okay, so let's move on then. Problem 4 is not terribly difficult for part A. Part B is a algebra sort of nightmare. You have to do lots of algebra. And so you should suffer through it once in your life just to see if you can. But the hard part is that you have lots of algebra. Because remember, for part A, it's going to be straightforward, but for part B, you have to square each of these expressions. So you're going to have to multiply out both of these trinomials, it becomes quite an exercise in algebra. Problem 5 is pretty straightforward. It's very much similar to the ones above. Problem 6, I believe, is straightforward. Maybe you can ask me a question. So what I would ask is, does anybody have a question about any of the numbers up through 7? I think most of the ones 1 through 7 are straightforward, and if they're not straightforward, we've given you enough hints. Okay, so then let's move on to problems 8 and stuff. So we did an example very similar to problem 8 in class last week, so I'll leave that to your own device. But what I want to look at is, I want to look at number 9. And number 9 and number 10 are very much the same in that they require that you remember some algebra. So let's look at number 9, and maybe you can do number 10. So let's say that number 9 and number 10 they require you recall some old fashioned algebra. Namely the following. Suppose I have a plus b quantity squared. So a and b can be anything. They can be numbers, they can be expressions. You guys learned back in the day that this is a plus b times the quantity a plus b, and then you taught you this little distributive trick called the FOIL method. And then hopefully you guys would remember that this multiplies out to this. So what happens is, when you're a student in algebra, and what happens often is that most students can move and read this left to right or top down. You're okay multiplying it out. But what a lot of students struggle with, and I would assume most of you do, because I did too, is most of us have trouble going the opposite way. Most of us have trouble factoring. Most of us have trouble looking at this line of reasoning and going from the bottom up. And in order to solve problems 9 and 10, you need to recognize a factorization that's of this form. So let's show you how it's done in problem 9. And then we'll move on. And hopefully you'll be good. Does anybody have any questions about this algebra before we move on? Going once, going twice. Yay. All right, good. So let's look at number 9. So our function f of x is log x minus 1/8 x squared. Now we want to determine the length of this curve. And so that means we need to first take the derivative, which is equal to 1 over x minus 1/4 x. And then we have to square this expression. And when we square this, depending on how you like to write these things out, every one of us is different. I like to write these, it's a little simpler to me if I combine this into one fraction. So that means I write this as 4 minus x squared over 4x. So you might need to convince yourself that that's the same thing. So I'll give you a moment for you to do the common denominator business. You don't have to do this, but for me, my brain prefers that we do this. Okay, so when I do that, that means that I'm squaring this expression. And it's helpful to note that if I multiply this out, I get 16 minus 8x squared plus x to the power 4 all over 16x squared. So what I'm doing right now is I'm doing the sort of the work that's necessary. Why am I calculating the derivative and why am I squaring it? Because that's in the formula for arc length. So don't forget the formula that we need. The formula we're going to use is the length from A to B, or excuse me, the length is the integral of this. So this is the integral that we are asked to calculate.
Wait, Professor?
Yes.
Where did the minus 8x squared come from?
Okay, so FOIL out the numerator or multiply out the numerator, just like I did on the previous page. Take the numerator, multiply it out. You have 4x times 4x, and since they're both negative, you add them together to get negative 8x squared.
Okay, thank you.
Yep, any other comments, questions? So again, let me reiterate, this problem, as I told you in the homework, I said this integral requires solid algebra skills. Okay, so this is the integral I need to calculate. And if we plug the respective pieces in, it's 1 to 2 of the square root of 1 plus what I have above. But I'm not going to write 1. I'm going to write 16x squared over 16x squared. That's a fancy way of writing the number 1. And then I'm going to plug this piece in. So I'm sort of planning ahead. Instead of writing the number 1, I'm writing it as so that it has a common denominator. So again, this is, you might have to take a moment to see what's happening here. Now, why would I write 1 that way? Well, I wrote 1 that way, so now I can easily combine the two fractions. I can add them. And what happens is, in the numerator, I have 2 terms with an x squared, so I can combine them. So what is 16 minus 8? 16 minus 8 turns out to be positive 8. So here's what happens on the next line of reasoning. And please pause me or stop me if there's a question you want answered. The next line is from 1 to 2. Now the denominator is going to stay the same. That's just 16x squared. But upstairs, if I jump back for a second, I have this 16 here as an x squared, and this is minus 8x squared. So I can combine those, and that means the numerator becomes 16 plus 8x squared plus x to the 4th dx. So let that marinate in your brain. Isn't this a fun problem? Who would have thought when they woke up this morning they'd be doing this wild ass stuff? Not me, I bet. That's what you're thinking. Some of you are like, I got to change majors. Basket weaving has no integration. I will go there. Okay, so here's the beauty. The beauty is if I figured out all that algebra, now this thing looks complicated, but it turns out it's not, because it's actually a case of what we call perfect square. Both the numerator, both this numerator and this denominator are perfect squares. So what do I mean by that? Well, if I go back a few slides, the numerator is of this form. The numerator looks like this, which means I can factor it into a perfect square. Now, of course, most of us don't remember all this crazy factorization, so that's why O'Grady has to put it on a problem to drive you nuts and make you remember it. My 8th grade algebra teacher would be so proud of us right now. So the numerator is nothing more than 4 plus x quantity squared. You could check that for yourself. And the denominator is nothing more than 4x quantity squared. So before you ask me how I got that, what I want you to do is take that numerator and square it. And then you should get the line above it. And then take that denominator and square it. And you'll see you get the line above it. This is heavy. Woo. Now, there's more to think about here. Here's another theme that I would encourage you to think about. This square root provides us a big sort of wall to get over. And what happens in this particular problem that is very fortunate, it's almost like we're lucky, is that what was inside of the square root was actually a perfect square. We just had to figure out how to recognize that it was a perfect square. Because if what's inside a square root is a perfect square, then they essentially cancel each other out, and all you're left with is 4 plus x over 4x. Square root kills square. And even more usefully, you can now simplify this expression. This is the same as 1 over x plus x over 4. Ain't this something? Any comments so far? All right, so we can now compute this integral. This is log x plus 1/8 x squared, evaluated from 1 to 2. You plug in 2, you get log 2 plus 4/8. Then minus, when you plug in 1, you get log 1 plus 1/8. And this simplifies to log 2 plus 3/8. And we have solved the problem. Wasn't that fun? Whew. Any questions, comments? This is sort of like a good test for you. You can say, man, if I can figure this problem out, I am a legend so far. Don't forget that the natural log of 1 is 0. That's why it disappeared. Any questions? All right. So the problem 10 is very much the same as this problem 9. So hopefully you can make some headway on it. Okay, so let's jump to the next problem. So we didn't mention this yesterday, or excuse me, last week, but if we look at number 11, it asks for what's called the surface area. So this requires the surface area formula. Now, we didn't derive it, and we're not going to because its derivation is almost, I don't want to say almost identical, but it's very similar to the derivation for arc length. So if I take a region or a curve and I rotate it, we already talked about how we can imagine we get a solid. So what the question then becomes is, what is the surface area of that solid? And, you know, if we go through much of the same reasoning that we went through with the arc length, so we come to the following. For a surface generated by rotating y equals f of x about the x-axis, the surface area is the integral from a to b wherever we start. And this has some similarities to our previous formulas, but it's different. You'll see the arc length piece in there. So this is a very sort of scary looking formula. Anybody have a question about this? Again, we could derive this by taking our surface, chopping it up, building Riemann sums, just like we've done numerous times already. But we're not going to do that because we've done it a few times. If you want to do that, you can do it yourself. What you need to be able to do is use this formula. So let's use it on a particular function, or at least I'll get you started. So for number 11, y equals 3 times the square root of x, which another way of writing that is 3x to the 1/2. which means the derivative is 3/2 x to the -1/2. And so if you differentiate that and square it, you get 9/4 x to the -1. So to get you started on this, what's the area? The area is the integral from 1 to 4, 2 pi f of x times this arc length piece. And if you plug in the appropriate pieces, this is 2 pi times the integral from 1 to the 4 of 3 square roots of x times 1 plus 9 over 4x dx. And then this looks overwhelming, but once again, if you remember your exponent properties, this integral is pretty straightforward. You can pull the 3 out and you're left with 6 pi integral 1 to 4. And then if you combine the radicals, you're left with x plus 9/4 dx if you distribute. So you guys can finish that. I can't steal all the fun from you, but we'll let you have that fun. Does anybody have a question about this? A comment? Going once, going twice. Sold. Okay, let's move on to 12 then, unless somebody wants to say something. Okay, so number 12, we want to find the arc length, but we run into a problem. If y equals x squared, then y prime is 2x, and y prime quantity squared is 4x squared. And so the length that we're asked to compute becomes a challenging integral, because when I plug it into the formula, I get this. So this is a challenging integral. To solve exactly. So instead, we will try to approximate it. So that's where we're at. We'll show you later on in the semester how to solve that integral exactly, but it is a challenging one. And maybe you looked it up already, and if you copied it down, you probably don't have much of an idea of what you were doing. It's very challenging. It requires some really ingenious tricks. We will show you it later. And then you'll say, oh, these tricks aren't that ingenious. They work for lots of things. And you're like, okay, cool. But we can't do that yet. So what we're going to do, since we don't know how to do it exactly yet, is we're going to approximate it. And what we need to do is we need to remember the definition of the integral is this limit of Riemann sums. So what I need to remember is I need to remember the following. recall the integral from a to b of f of x dx is approximately the sum, k goes from 1 to say 4, we'll use 4, I asked you to use 4, of f evaluated at x sub k times delta x. Now, what do these things mean? Well, this is when delta x is b minus a over 4. And then x sub 1 is a plus delta x. X sub 2 is a plus 2 delta x. X sub 3 is a plus 3 delta x. And then x sub 4 turns out to just be b. So I can't, this was the stuff we spent a lot of time in Calc 1 talking about. I hope that you will draw pictures and sort of connect it with our problem. So let's apply these ideas, these Riemann sum ideas, to our particular problem. And don't forget what all this means. So we'll draw the picture of this for our particular problem in a second. So if we apply all that for our integral, what is our integral? Our integral is integral from 0 to 1 of 1 plus 4x squared dx. So this is approximately the following. It's going to be delta x times f of x sub 1 plus f evaluated at x sub 2 plus f evaluated at x sub 3 plus f evaluated at x sub 4. So let me remind you what everything is here. Our function that we're interested in, f of x, is this. Delta x is just going to be 1/4. Because 1 minus 0 over 4 is 1/4. So if I come up here and plug that in, what I'm really asked to compute, this is 1/4. Then this is f. What is x sub 1? Well, x sub 1 is just 1/4. X sub 2 will be 2/4. X sub 3 will be 3/4. And then x sub 4 is 4/4, but that's just 1. Now, the easiest way I can convince you to see this is to draw a number line. This is what made it click for me many years ago. If I have the number line between 0 and 1 and I want to divide it into 4 pieces, I cut it in half, I have 1/2. Then I cut these pieces in half, I have 1/4. And then I have 3/4. So that's where I'm getting these numbers from. Anybody have a question or a comment? So that means I have to plug f, I have to plug, 1/4 in here plus 2/4, which is the same as 1/2, plus 3/4, and then lastly plus 1. So there's a real easy way of doing this. It's called use a calculator. So let me show you how to do it on Desmos. So if I go to Desmos and I put my function in here, it's this. And I'm interested in getting a Riemann sum to look at the area under the curve. So what I'm going to do is I'm going to draw one here. Hopefully it'll make sense to you. Actually, you know what? Let's use GeoGebra. It's better at doing this. So let's go. Use GeoGebra. I want the 3D one. So GeoGebra will let you define a function. So let's define our function we want to integrate. It's the square root of 1 plus 4x squared. And then GeoGebra also has a very nice built-in function that will give us Riemann sums if we want. So what I do is the function you just type is rectangle sum, and you'll notice that it autofills for me. And so I want to do a rectangle sum, and then I have to tell it what's the function, where am I starting, and where am I ending. I'm ending from 0 to 1. And then the number of rectangles, and then which do I want to use, a left, right Riemann sum. So I'm going to use the right Riemann sum, and it gives me the number 1. So what you could compute by hand is the area of these 4 rectangles. Now the nice thing is GeoGebra did it for us. It added them up. It computed these 4 rectangles, excuse me, the area of the 4 rectangles, and added them together, and we got this number 1.64277. Does anybody have a question about this? So again, if I go back to my whiteboard, if I go to a calculator, let me separate this, and I plug these numbers into my calculator, what I end up getting is I get that this is 1.6427791. So that is the approximate length of my curve. Now, what you might be thinking about, you might be thinking ahead, and you might be saying, oh, you know what? That's probably a bad approximation, because you see these rectangles aren't very, there's lots of error, and that's okay. If we increase the number of rectangles, we get a better and better approximation. Does anybody have a question about this? So this is what I'm hoping that you guys can figure out how to do on your own for problems 12 and 13. Does anybody have a question? Comment? So I think this is a good place for us to start. I hope that you guys will get to working on these assignments, and you'll email me if you have any questions. Some of you did email me questions about these problems. If we didn't answer your particular question, please resend the email, and I can either type you something up or make you a little video and send it along. But I think the best way for us to get any good experience out of this is for you guys to go try it now. Or maybe not now, but later today, and then ask questions if you're still stuck. Does anybody have any questions about where I got any of these numbers on the whiteboard, or how I got them? I highly encourage you play around with GeoGebra or Desmos. It can make doing this super, super easy. For example, let me beat the dead horse real quick. If I go to Desmos, this is very easy to do in Desmos too. If I go to f of x and I plug my function in, remember, the number I was looking for is I was looking for 1/4, and then I was times f of 1/4 plus f of 1/2 plus f of 3/4. Whoa, that's not good. Plus f of 3/4 plus f of 1. And you'll notice that on Desmos, if I just type that in, just like I did on the whiteboard, I get the same answer, 1.6 something. Does anybody have a comment or a question on this? All right, well, if you guys don't have questions, oh yeah, someone who. Yeah, so Joel's asking is, we just did 12, 13 pretty similar. Yes, 13 is almost identical, it's just your function will be different. For 13, the function you're integrating is going to be different because you're studying a different function. And in 12, you're doing arc length. In 13, you're doing surface area. So if I give you a hint on that, oh, wrong button. So if I go to new share, so for 13, what you're interested in is y equals e to the x, I believe, right? Yeah. So what's the derivative of that? The derivative is e to the x, and so the derivative squared is e to the 2x. And so we want the surface area, which for this problem will be integral 0, 1. And then for this guy, it's 2 pi f of x. Well, excuse me, I shouldn't say f of x. It's let me back up. I don't want you to use this in two different contexts. So it's 2 pi times the function, which in this case is e to the x, plus 1, the square root of 1 plus the derivative squared. So you get this inside. So this is going to be approximately 1/4, and then it's f of 1/4 plus f of 2/4 plus f of 3/4 plus f of 1. But here, what is your function? The function you're interested in is 2 pi e to the x times this quantity. So you have to make sure you do the right function. So that's how you would do 13. Make sure you understand that, though. Don't just copy down what I gave you. Make sure you get it. Any questions about this problem? Any other questions? All right, well then in 5, 4, 3, 2, 1, I will end this recording now.